45 years after the eruption, scientists are still watching as parts of the area rebound.
The ground beneath Mount St. Helens has been shifting with a pace that has startled even the most seasoned volcanologists. Deep below the rugged slopes, a reservoir of molten rock is swelling more rapidly than anticipated, forcing the United States Geological Survey to issue a rare red alert. This isn't just another incremental adjustment in volcanic activity. The data pouring in from GPS stations, seismographs, and satellite-based interferometry has revealed a marked and accelerating inflation of the volcano's magma chamber. Scientists tracking the phenomenon are seeing deformation patterns that suggest a significant injection of magma from deeper within the mantle, pushing upward with relentless force. Before we start, smash the like and subscribe buttons for more updates. For decades, Mount St. Helens has been one of the most closely monitored volcanoes in the world. Since its infamous 1980 eruption, the region has been blanketed with a dense network of sensors designed to detect even the slightest tremor or shift. This time, the signals are unmistakable and far from subtle. Instruments anchored into bedrock have recorded several centimeters of uplift over mere weeks, an alarming rate in geological terms. That speed matters, because magma chamber expansion at such a pace can dramatically increase the potential for an eruptive event. It suggests that the volcano is not simply breathing in its usual cyclical pattern, but undergoing a genuine and significant recharge. The red alert designation is more than just a warning flag. It reflects a combination of seismic intensity, deformation rates, and gas emissions that meet the highest threshold of concern. Sulfur dioxide measurements have spiked, and plume analyses indicate fresh magma is close enough to the surface to alter gas compositions measurably. The chemistry of these gases tells scientists a story about the magma's depth, temperature, and movement, and right now the story points toward a system under pressure. As magma pushes upward, it fractures rock, creating a swarm of small earthquakes that have been clustering beneath the mountain at depths of 3 to 6 kilometers. These seismic swarms aren't random. They map out the intruding magma's path. Such rapid expansion of a magma chamber doesn't happen in isolation. It exerts enormous force on the surrounding rock strata, warping the landscape in subtle but measurable ways. In some cases, this deformation can destabilize slopes, increasing the risk of landslides or rockfalls even before any eruption occurs. For Mount St. Helens, with its history of catastrophic slope failure in 1980, that risk cannot be ignored. The north face, which collapsed in that historic event, remains a geomorphological weak point. Pressure from below could alter stress distributions along the edifice, potentially setting the stage for renewed instability. From a scientific perspective, the speed of this inflation has implications for how magma is moving through the crust. A gradual rise might indicate a slow trickle feeding the chamber, giving gases time to escape and pressures to equilibrate. But the current pace suggests something more forceful, a surge of melt driven by buoyancy and pressure differences that could be tapping a deeper magma reservoir. This has the potential to overwhelm the system's ability to vent gas naturally, locking volatile compounds inside the magma. When gases are trapped, they act like compressed propellant. If the system fails, the resulting release can be explosively violent. Local geologists are particularly focused on the nature of the magma itself. Past eruptions of Mount St. Helens have varied in style and composition, from relatively fluid basaltic flows to highly viscous dacite domes. The current gas ratios and seismic signals lean toward an andesitic to dacitic composition, which historically correlates with more explosive eruptive behavior. Magma of this type traps gases more effectively, increasing the potential for powerful blasts that can project ash, pumice, and pyroclastic flows over vast distances. The swelling magma chamber also interacts with the hydrothermal system embedded within the volcano's flanks. As magma intrudes, it heats groundwater, increasing steam pressure in fractures and cavities. This can cause phreatic explosions, steam-driven blasts, that occur without any direct eruption of magma. Such events are unpredictable and can happen with little warning, endangering areas close to the summit. Steam explosions can also destabilize overlying material, carving out new craters or initiating debris flows down the slopes. One of the more sobering aspects of this accelerated inflation is the strain it places on hazard forecasting. Volcanic systems are inherently complex, with multiple feedback loops that can either amplify or dampen unrest. The rapid pace of change at Mount St. Helens means models must be updated constantly, with each new data point shifting the probabilities of different scenarios. The USGS response teams are now working around the clock, running simulations that integrate seismic data, gas measurements, deformation rates, and thermal imaging from satellites. Each scenario presents its own set of implications, and the margin for error narrows when the system is evolving daily. The implications extend far beyond the crater rim. The Cascades region, stretching from Northern California into British Columbia, is a volcanic arc capable of producing significant eruptions. An increase in activity at Mount St. Helens prompts closer scrutiny of neighboring volcanoes such as Mount Adams and Mount Hood, which share similar magmatic plumbing systems. While each volcano is distinct, deep magma injections can sometimes signal broader tectonic or magmatic shifts affecting multiple peaks along the arc. This raises questions about whether the current surge is a localized event or part of a regional magmatic episode. The red alert status also shifts priorities for agencies managing the surrounding lands. The Gifford-Pinchot National Forest and other recreational areas near the volcano may see access restrictions as officials assess potential risks. For scientists, however, the restriction of public access can be an opportunity. It allows for the deployment of additional instruments without interference and reduces the risk to the public if conditions deteriorate rapidly. Helicopter overflights are being scheduled more frequently to capture high-resolution thermal and photographic imagery of the summit and crater floor, providing critical insights into surface changes. Another dimension of concern lies in the volcano's ability to produce far-reaching ash clouds. Depending on wind patterns, an explosive eruption could send ash eastward across Washington, Idaho, and beyond, affecting air travel and sensitive infrastructure. Ash can damage engines, disrupt power systems, and contaminate water supplies. While these impacts are potential, rather than imminent, the rapid expansion of the magma chamber makes contingency planning an urgent matter. Emergency management agencies across the Pacific Northwest are revisiting eruption response protocols, ensuring communication lines remain open between scientists, local officials, and the public. From a geological time perspective, Mount St. Helens is an active young volcano, still in a vigorous phase of its life cycle. Its behavior now is part of a long continuum of construction and destruction, as magma builds the edifice only for eruptions to dismantle parts of it. The present rapid inflation may be one more step in that cycle, but the scale and speed of this episode set it apart from the more measured growth phases seen in past decades. This is why volcanologists are treating the situation with heightened urgency. The magma chamber's growth is not just a matter of volume, but also of distribution. High-resolution imaging suggests that the expansion is asymmetrical, with more uplift concentrated on the southeastern flank. This uneven inflation can create localized stress fields, potentially reactivating old faults or creating new fracture zones. These fractures in turn can serve as pathways for magma migration, influencing where and how any future eruption might break the surface. Understanding these pathways is critical for hazard mapping, as they can shift the zones of greatest risk away from the summit to other parts of the volcano's slopes or even beyond. In this evolving situation, each new measurement is a piece of a complex puzzle. The satellite-based interferometric synthetic aperture radar INSAR imagery reveals patterns of uplift that match well with ground-based GPS data, reinforcing the conclusion that the inflation is both real and accelerating. Seismic tomography, essentially creating a 3D image of the subsurface using earthquake waves, has begun to highlight areas of partial melt feeding into the main chamber. These technical insights not only confirm the magma's presence, but also provide clues about its temperature and composition, factors that directly influence eruption style. Even without immediate eruption, the current rate of magma intrusion means that heat and pressure will continue to build beneath the volcano. This has the potential to reshape the internal structure of the mountain over time, altering the geometry of the magma chamber and the conduits leading from it. Once those conduits evolve, they can change how the volcano behaves in future eruptive cycles. This makes the present moment not only a matter of short-term hazard management, but also a critical period for understanding the long-term evolution of Mount St. Helens. Scientists working in the field have expressed both professional excitement and professional caution. The chance to study a major magmatic intrusion in near real time is invaluable for volcanology, offering data that can refine models and improve forecasts for volcanoes worldwide. Yet the same forces that make this a rich scientific opportunity also carry the weight of potential disaster. The balance between observation and preparedness is delicate, and the red alert status reflects the recognition that conditions could change rapidly. The broader implications also touch on the resilience of nearby communities. While the current discussion centers on the volcano itself, the surrounding ecosystem and human infrastructure are intertwined with its activity. Rivers that drain the mountain can be affected by volcanic heating, altering snowmelt patterns and potentially mobilizing debris flows. Roads and bridges built along these valleys may face sudden closures if monitoring indicates an increased risk of lahars, fast-moving slurries of mud and rock triggered by volcanic activity. These hazards can occur with or without a full-scale eruption, adding another layer of complexity to planning efforts. Beneath the quiet forests and rugged ridges surrounding Mount St. Helens, a deep and invisible transformation continues to unfold. The magma chamber's rapid expansion is not simply a matter of molten rock pushing upward. It is a cascade of interconnected processes that ripple through the entire volcanic system. As new magma intrudes from deep within the mantle, it displaces older, partially solidified material, melts surrounding rock, and alters the pressure gradients that have kept the volcano in relative equilibrium. This rapid shift in internal dynamics makes the current situation unusual in both speed and intensity, a combination that leaves little margin for complacency among scientists. The flow of magma into the chamber is not smooth or uniform. It pulses in waves, driven by fluctuations in pressure within deeper magma reservoirs. Each surge is accompanied by its own seismic signature, with clusters of small, shallow earthquakes punctuated by deeper, more resonant tremors that hint at movement many kilometers beneath the surface. These deeper events are particularly significant because they indicate that the source of the intrusion may extend into the upper mantle, a reminder that the roots of the volcano tap into a much larger magmatic system. When that system mobilizes on such a scale, it can feed prolonged periods of unrest, even if the immediate surface remains outwardly unchanged. The shape and structure of the magma chamber itself add complexity to the picture. Rather than being a single spherical pocket of molten rock, the chamber is a network of interconnected, melt-rich zones separated by partially solidified crystal mush. This configuration means that magma can accumulate in one area before migrating laterally to another, sometimes bypassing the most direct route to the surface. Such lateral movement can change the location of maximum uplift on the volcano's flanks, making it harder to pinpoint exactly where pressure might eventually breach. In past events, magma movement at Mount St. Helens has surprised observers by shifting toward weaker points in the edifice rather than rising directly through the summit conduit. The pressure building within this complex structure is not only mechanical but also chemical. As magma ascends, the decrease in confining pressure causes dissolved gases, water vapor, carbon dioxide, sulfur dioxide, to exsolve, forming bubbles within the melt. These bubbles expand rapidly, increasing the magma's volume and viscosity. The combined effect is like shaking a sealed soda bottle. The more bubbles trapped inside, the greater the potential for an explosive release. If the magma chamber's expansion continues at its current rate, the proportion of gas-rich magma could rise sharply, heightening the system's volatility. Monitoring these changes requires a fusion of techniques. Ground-based seismic arrays capture the rumble of moving magma, while tilt meters detect subtle shifts in the volcano's slopes. Thermal cameras mounted on drones and aircraft reveal hotspots on the crater floor, areas where heat from below is penetrating to the surface more strongly than before. These zones often correlate with fractures or vents that could serve as outlets for gas or magma. Observations from multiple instruments are cross-checked and combined, building a layered picture of the volcano's condition. Every dataset reinforces the conclusion that the current inflation is not part of a slow, decades-long cycle, but rather an accelerated event with uncertain consequences. The geographic context of Mount St. Helens further amplifies the importance of this red alert. Positioned within the Cascade Volcanic Arc, the mountain sits atop a subduction zone where the Juan de Fuca Plate dives beneath the North American Plate. This tectonic arrangement continuously supplies heat and magma to the crust, fueling a chain of volcanoes that includes Mount Rainier, Mount Hood, and Mount Shasta. A surge of magmatic activity at one location can sometimes signal broader changes in the arc's behavior, as shifts in deep magma supply or tectonic stress propagate along the plate boundary. Although there is no immediate evidence of synchronized unrest among other Cascade volcanoes, the regional monitoring network is on heightened watch for signs of correlated activity. For the scientific teams working at the mountain, the accelerated chamber growth also represents a rare and valuable natural laboratory. In most cases, magma intrusions of this magnitude occur over timescales too long to observe in detail, leaving researchers to piece together their history from rock records. Here, they have the opportunity to witness the process in real time, testing models of magma ascent, chamber pressurization, and surface deformation. High-resolution mapping of the uplift zone, combined with seismic tomography, could refine the understanding of how magma navigates complex networks of fractures and conduits. These insights may one day improve forecasts not only for Mount St. Helens, but for volcanoes around the world. The human dimension of this event cannot be overlooked. Even without an eruption, the heightened unrest disrupts life for those who live, work, and travel near the mountain. Access roads may be periodically closed, recreational permits suspended, and airspace restricted. Tour operators, park services, and local businesses dependent on seasonal visitors must adjust plans on short notice, knowing that safety takes precedence over tourism. Residents in surrounding communities are once again hearing the low hum of helicopters conducting overflights and the periodic thud of seismic activity as detected by sensitive instruments. Subtle reminders that the volcano is restless. Hydrological changes are another emerging consideration. The intrusion of heat from below can accelerate melting of snow and ice on the summit and upper flanks, even outside the typical melt season. This water, combined with volcanic sediments loosened by ground shaking, can feed sudden, fast-moving lahars that race down river valleys. Past lahars from Mount St. Helens have traveled tens of miles, reshaping landscapes and altering river courses. Monitoring stations along key waterways are now calibrated to detect sudden spikes in flow rate or turbidity that could indicate such events in their earliest stages. The velocity of the chamber's expansion has also prompted deeper examination of potential triggering mechanisms. Some volcanologists are exploring whether shifts in regional tectonic stress, possibly linked to recent seismic events elsewhere along the Pacific Northwest, have opened pathways for magma to rise more quickly than before. Others are considering the role of buoyancy-driven instabilities within the deeper magma reservoir, where variations in composition or temperature could have set off the upward surge. The fact that these processes remain partly mysterious underscores the challenge of forecasting volcanic behavior. Even with decades of data, each episode can introduce new variables that defy previous patterns. Advanced computer modeling has become a cornerstone of the current response. Using supercomputers, scientists can simulate the volcano's internal plumbing and test how different rates of magma influx affect pressure and stress distribution. These models incorporate real-time data streams from the field, allowing for continuous refinement as new measurements come in. By running thousands of scenarios, researchers can identify conditions that might lead to different outcomes, whether a slow decompression through minor eruptions or a sudden violent release. The goal is not to predict a specific date of activity, but to narrow the range of plausible futures and ensure readiness for any of them. Mount St. Helens history offers both context and caution. While the catastrophic 1980 eruption is the most famous, the volcano has experienced numerous other episodes of dome building, lava extrusion, and minor explosive events. In many cases, significant chamber inflation preceded surface activity, though not always at the speed seen today. In 2004, for example, the volcano underwent a period of sustained growth of a lava dome within the crater, fueled by magma rising at a moderate pace. That episode released pressure gradually, preventing a major explosive event. The current rate of inflation, however, surpasses that of 2004 by a notable margin. raising questions about whether a similar slow release is even possible under present conditions. The interplay between magma chamber growth and the volcano's structural integrity is a central concern. As pressure mounts, it can exploit weaknesses in the edifice, fractures from past eruptions, zones of hydrothermally altered rock that are weaker than surrounding material, or the interface between different lava flows. If such a weakness connects to the surface, it can act as a vent for gas and magma. If it fails catastrophically, it can trigger sector collapse, sending massive amounts of rock and ash downslope. What was once purely a force of creation can now threaten the fabric of human life and economy. If you liked this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us. What are your thoughts on Mount St. Helens alert? Will eruption happen soon? We want to hear from you. Thank you for watching, and see you next time.